know, it's a phone. What's so complicated about the audio interface? Well, we have typically at least three analog outputs. There is usually a headphone jack for like earphones or a headset. There is the actual speaker that is points at your ear when you use the phone, the ear speaker, and the ringtone speaker, which is at a different location to play the ringtones or music for whoever wants to listen to music on these crappy speakers. Then you have two analog inputs, the built-in microphone and the microphone that is connected externally in the headset. Well, then you need to somehow connect the GSM modem, which I'm not sure what I would call most cases. I would just say in a number of cases it's analog, so they actually connect line-level analog audio or even microphone-level audio between the baseband processor and the baseband processor and the audio codec that's on the application processor side. This is obviously very simple, because if you take an existing mobile phone chipset that's used in a feature phone, it already has the input and output of analog audio. So you basically just wire that to a sound card kind of device, which is the audio codec that is connected to your application processor, and you have it working. But then analog audio has all kinds of issues. So some devices have digital interfaces here at the cost of significantly increased software complexity, because then you end up having PCM buses that sometimes are clocked by the GSM modem, but sometimes are clocked by maybe the system on a chip and so on. There's all kinds of interesting things. In any case, even if the GSM modem uses an analog interface, you still have two PCM buses. So PCM, pulse code modulation, that's basically digital audio interface, a very basic one. You have one between the system on a chip and the audio codec. So this is like on your PC with a sound card. You have your main CPU, and the main CPU somehow has a sound card attached to it, and then there's some interface between your CPU and the sound card. And that interface could be AC97, could be Intel high definition audio in the PC side. It's just a different interface in the phone. But it's basically for playback of digital audio from the application processor into the analog domain, and vice versa. So the other PCM bus that you see is between the Bluetooth and the codec, because there are Bluetooth headsets, and the Bluetooth headsets transmit audio data, and that audio data in such a battery-constrained, low-power mobile device, you don't want to go from the Bluetooth chipset through the UART into your application processor, into software, and then from there send it out again to the actual audio codec. So that's why you have a direct PCM interface where the Bluetooth can talk directly to your audio codec. This is the audio routing diagram of the codec chip that's used in the OpenMoko, both of the hardware generations. So I'm not going to go into the details, but basically you can see my mouse pointer here. Like we have from GSM comes in here, for example, in RXP, RXN. The headset microphone is connected here. The handset microphone is connected here. And then you have various inputs and switches and amplifiers, programmable amplifiers, programmable mixers. Here you have the analog digital converters. And on the right-hand side, you have all the different outputs, like the earphone speaker, the headset speaker, and the earpiece of the handset. And each of those tiny little spots in that diagram, they correspond to something that software can configure. So if you map that to ELSA, which we obviously do in which OpenMoko, but we did, I'm still talking about we because I was there when it was done, so which OpenMoko obviously did, if you want to represent this properly in a contemporary Linux system, you want to have an ELSA mixer with all those controls. So you have actually 94 controls in the ELSA mixer on a phone, right? And believe it or not, it can get fairly interesting to play with these things, because suddenly, if you have full control of this, you can do things like play back an MP3 file and feed that into your GSM voice call, so play back something, or record from the call, or do all kinds of interesting things. But it's possible, it's there. And this is not particularly complex, right? So OpenMoko is just as an example. This chip is used in a number of different devices, and similar chips are used in all smartphones. So there's a lot on the audio side just for that. The digital part is not, like here on the bottom you have the PCM to CPU and to Bluetooth part. It's not, like all the details have been left out. So this is already simplified to some extent. So, which brings us to OpenMoko hardware. So I'm going to look at 3 different hardware products or product families. First one is OpenMoko because it's interesting for people who are interested in this topic but who don't necessarily work at a mobile phone manufacturer. Because everyone can study the systems and the circuits and the schematics because the schematics are available. Full schematics in quotes, well, detailed schematics, but the GSM baseband side cannot be there because of the closed nature of particular commercial entities in the semiconductor business for mobile phones. But that, like, if you want to understand the functionality of the phone, the baseband side, you just look at it as a modem. It connects to a serial line, you get analog audio data in and out, and that's about it, what you need to care about it. If you look at it on a high-level, simplified diagram, how all this looks. So basically you have the system on a chip in the center. In this case, what is used here, well, Samsung actually does, sometimes they call it S3C, sometimes they call it SC3. They don't actually know which one it should be called, so don't be surprised by that. So this particular component, it's one component that is 13 by 13 millimeters, and I think maybe 1 millimeter in height. I don't remember exactly. And in that single package, there is not only the system on a chip, but also the flash and RAM memory. It's what's called a multi-chip package. So you have multiple dies inside one physical package to save physical, what's called PCB footprint. So you save space on your board design. Then you have the number of controllers or interfaces externally. So there's a NOR flash chip. There's some more SDRAM externally because 64 megabytes is not enough for everyone. There's an I2C interface that connects to the power management unit over here. The Wolfson codec, which is the audio codec on the lower left-hand side. And then there is the mono amplifier, which is external to the Wolfson codec. There's another amplifier, so you can hear your ringtone even louder. Then on this side we have the Calypso, which is the GSM baseband processor. That connects using a UART, a serial line, to the application processor. And to another UART we connect the GPS module. I didn't talk about GPS before, not all the phones have it, but those phones that have it, it's always connected to a UART, but not always to a UART of the baseband, of the application processor. Sometimes they connect the GPS to the baseband processor. I think the technical reason for doing so is because they don't have enough UARTs on the application processor. But it makes me extremely worried if the GPS is connected to the baseband side. And then I should trust the device, it's like, the GPS data first goes into the GSM modem where all the, deep secret GSM stack is running. And then the GSM data is forwarded to your application processor. So if you switch it off on the application processor side, is it really switched off, or does it still feed the location into the GSM modems? Anyway, so we have an SDIO interface which connects to a Wi-Fi module, and we have a USB connect. This is not true. Is it? Oh, yes, it is actually true. Yes, it is true. It is USB connected, the Bluetooth, in this case. Yeah, because we ran out of UARTs. There is another. There is another connection between the Bluetooth module and the audio codec over here, but the person who drew that diagram, obviously it's hard to draw a line all across the diagram, but that's the PCM bus between the Bluetooth and the codec over here. Yeah, we have an LCD controller that is obviously connected to the LCD, not disconnected, and there is, oh no, sorry, no, it's actually true. The LCD controller is not used, the built-in LCD controller of the SoC is not used in this hardware revision, but there is a graphics accelerator, in quotes, connected to a display module. This is the LCD display. And that one, again, has an SDIO interface, which connects to the SD slot, because, well, the SDIO controller here is used for the Wi-Fi interface. So you see the kind of problems. Your hardware interfaces are limited in number. You add more and more peripherals. So, where do I move it? Do I shift it here, but then I lose this? Where can I connect there? Where can I connect that? No. Okay, this is that's the overview diagram. Now, if you look at the actual board, so this board, I choose this picture because the quality is better than the later pictures. This is an old version of the hardware. So this is not the device you will get when you buy an OpenMoko system today. This is an old design, and I just put this up there to see, so you can see how much, like, how tightly squeezed the BGA packages are, like in this area, for example, and how full the board is in general. So this entire section over here on the left-hand side is the application processor section. We have the system on a chip here. This is the one which does not have the integrated flash and SDRAM. So we have the flash here, SDRAM here, and the S-Media here is the graphics accelerator. This one, the PCF50633, is the power management unit, which is the same that is used in the iPhone, by the way. We made NXP to open the datasheet, so I'm sure people can have creative uses for that. That's the Wolfson codec for the audio side, and that one, I think, is that's the audio amplifier over there. And the section which has the frame for the shielding cover over here is the actual GSM modem side. This one is the baseband processor, then we have the DSP over here, some flash and RAM in one package down there, and this is RFPA, I think, over here, basically. And we have the section here, which is completely covered, is the GPS unit that is separately shielded because GPS has very sensitive signals. So this is basically how something like this looks like. Let's look at some other hardware. The Motorola EZX hardware, which obviously has only one W, as I recognize now, has multiple generations. There is generation number 1, which includes the A760, the A768, the A780, and the E680. All of these devices are not very commonly known in the Western world. They're mostly sold in the Asian market. The only thing that ever was, I think, regularly sold in Europe was the A780. And the hardware of these devices is fairly well known because the schematics have leaked quite some years ago. So people have been able to study them. In those devices, all the Motorola devices, for example, we have a couple of key characteristics. One of them is that the audio is routed digital, so we don't have analog audio between the baseband side and the application processor side. It's PCM interface. All of these have at least one custom ASIC, which is not a standard component that you could otherwise use. It's the power management unit in those devices. What else is characteristic about Motorola? And they have a very weird, at least the generation 1 and generation 2 have a very weird interface to talk to the modem. They use USB with some additional handshake lines, and it's like USB with flow control over GPIO, something like that. It's really nasty. The generation 2 phones are a little bit more known, as in the actual devices are a little bit more known in the Western world. I think some of them have been sold in non-Asian countries. The schematics of these, for some of them, also have leaked, so the hardware is also fairly well understood. And then it's the generation 3 hardware, for which the schematics, unfortunately, I have not seen yet. Those include the E8, Z6, V8, and so on and so on. These are more current devices. In those devices, however, it's very hard to do any hacking by yourself because they have a custom smartphone on a chip component. It's basically a single component that includes the system on a chip for the application processor side, which is an ARM11. The system on a chip device for the baseband side, which is an ARM9. 2 DSPs. The analog digital converters for the baseband side, and so on. So basically, it stuffed the entire system into a single chip.